Welcome to this explainer. Today we're taking a completely different approach to map making. We're not looking at it as some subjective art form, but as a rigorous, data-driven science. Seriously, if you've ever glanced at a map and instantly understood the terrain, or, been totally lost trying to match a tiny legend to this messy maze of colors, you've actually experienced cartographic usability firsthand. And today, we are taking all the guesswork out of that experience. So let's dive right in and totally shatter this illusion that effective maps are just, happy design accidents. Because they're not. They are highly engineered interfaces. We're not just going to chat about what looks pretty. We're answering a really fundamental prompt here. How do we mathematically prove that a map actually works? We'll be pulling directly from some cutting-edge cartographic research to see exactly how the pros do this. But first, we really need to nail down what we mean when we say cartographic usability. Simply put, it's the measurable effectiveness and efficiency of a map. Think of the map as this critical interface bridging the gap between raw geospatial data and human cognition. So we're going to explore the actual scientific process used to evaluate how our brains interface with these geospatial tools, literally how we turn raw visual stimuli into working memory. To get there, we'll be running through 4 key protocols: planning the usability study, the eye-tracking interface, visualizing gaze data, and finally, the statistical proof. All right, starting off with Section 1, planning the usability study. You see, every good scientific diagnostic has to begin with a precise plan. You need a clear research question and a highly testable hypothesis. You can't just ask people, hey, is this map easy to read? That's way too broad. You need a targeted approach. So we're going to follow a fictitious case study throughout this explainer to show you how this works. We're testing a very specific hypothesis. Do output medium and color scheme influence the correct recognition of spatial patterns? In plain English, if you're hunting for hotspots of data on a map, does it actually matter if you're holding a physical piece of paper versus looking at a screen? Or what if the map uses red, green, or blue color schemes? Now, the absolute most crucial part here is cleanly separating our inputs from our outputs. We have our independent variables. These are the factors we actively change, right? Like swapping a paper map for a digital screen or changing a red theme to a blue one. And then we have our dependent variable. That's the measured outcome resulting from those changes. In our case study, that's just the sheer number of hotspots our user correctly identifies. It's exactly like tuning the parameters of an algorithm. You absolutely have to lock these variables down to get reliable data. Okay, next up, we have to pick our testing environment. Basically, we're deciding between the sterile, hyper-controlled vacuum of a laboratory and the unpredictable chaos of out in the field. Laboratory studies, they give us an incredibly controlled space to isolate specific variables. Everyone uses the exact same monitor, in the exact same lighting. Boom. Field studies, on the other hand, test users in their natural environment, like, say, using a hiking app outdoors. Now, glare and distractions introduce some totally unpredictable variables, sure, but they offer this invaluable real-world context that you just can't get in a lab. And hey, get ready for a pretty surprising piece of math. You'd probably think you need hundreds of people to find the usability flaws in a map, right? Well, according to Nielsen and Landauer's foundational models on usability, a single person will actually spot about 30% of the errors. Bring in just 5 people, that jumps to 85%. And by the time you hit roughly 15 test subjects, the error detection rate practically flattens out at nearly 100%. That is wild. You literally only need about 15 test subjects to detect almost all the usability errors in an interface. Talk about efficiency built right into the methodology. Moving right along to Section 2, the eye-tracking interface. Now we get to look at the actual hardware used to measure human cognitive processing. We're stepping out of the planning phase and getting straight into the physical biology of map reading with eye-tracking studies. This is so cool because we don't just ask users where they looked, we track their actual biology. The system blasts this invisible infrared signal that bounces right off the human cornea. Then a specialized camera captures that reflection to pinpoint the exact orientation of the pupil. And it's running at blistering capture rates between 60 and 250 Hz. We're talking about tracking visual attention in real time. To really grasp why this matters, try thinking of human biology kind of like computer hardware. Data can only be downloaded into your sensory memory when the eye is stationary in what scientists call a fixation. These usually last a little longer than 200 milliseconds. But when your eye jumps from one side of the map to the other, making a rapid movement called a saccade, your cognitive system is effectively offline. Yeah, zero visual information is acquired during a saccade. None. So by capturing these rapid biological signals, we can decode massive amounts of usability data. For example, if we see a super high frequency of saccades,
That means search efficiency is really low. The user is just hunting around for information. If we notice abrupt angle changes in their eye movements, the user is probably really confused about the task. And crucially, if we see frequent eye jumping, back and forth between a map area and a legend, well, that practically screams that the design is way too complex or ambiguous. Which brings us to Section 3, Visualizing Gaze Data. Let's process all that raw biological data. We basically translate thousands of those eye coordinates into these futuristic digital overlays that reveal the invisible landscape of human attention. We've got 3 primary analytical engines here. First up, the gaze plot. This maps out the sequence and duration of saccades, showing exactly where a user looked first, second, third, and so on. Next, the heat map. This one strips away the timeline and aggregates fixation intensity, so those darker areas, that's where collective attention was basically trapped. And finally, the bee swarm. This pinpoints the exact individual data acquisition nodes.
But hold on, because there's actually a massive catch to all this tracking. According to visual attention research, including some really foundational work by Yarbus, to get clean data from these heat maps, you have to give users highly specific tasks. If you just toss a map in front of someone and say, hey, look at this, their undirected attention is completely chaotic. The resulting gaze plots will just be a useless, messy web of random saccades. Top-down visual attention demands a specific task if you want to get any usable data out of it.
All right, we've made it to Section 4, the statistical proof. Because here's the thing, observation alone just isn't science. We might look at a heat map and think it favors one design, but we need undeniable math to actually validate that. This is the definitive 5-step algorithm for hypothesis testing, and it takes us all the way from raw usability data to objective scientific truth. You can't just glance at the numbers and declare victory. No way. You have to formally formulate hypotheses, set a mathematical error threshold, pick the right statistical test, run those calculations, and then, finally, make a data-driven test decision. In statistics, we always start out as the ultimate skeptics by assuming what's called the null hypothesis. Now, the null hypothesis stubbornly states that your brilliant map design had absolutely zero effect, and any success you saw in user testing was just a random fluke. So to prove your map actually works, you have to mathematically dismantle this null hypothesis. Let's see how this ties back into our original case study, all right? Looking at the raw data, users hunting for hotspots on physical paper maps had a 90% success rate, so 90 correct out of 100. Users on digital screen maps had an 83% success rate, 80 correct out of 96. Now, at first glance, paper looks like the clear winner, right? But wait, remember the null hypothesis. We have to run a specific formula, in this case, a chi-square test, to prove this difference isn't just some random blip in the data. And the magic number for that proof? It's 5%. 5% or a 0.05 p-value is the ultimate significance threshold our data has to cross in the social sciences. When we actually ran that chi-square test on our paper versus screen data, the resulting p-value was 0.161. Since 0.161 is higher than 0.05, well, we failed to beat the threshold. Scientifically speaking, that difference we saw earlier was completely random. Neither map medium was actually proven superior in that specific test. As we wrap up this explainer, I want to leave you with this thought. Cartography is no longer just about geography. It is literally about hacking human cognition. The next time you blindly follow a GPS map or zoom into a weather radar on your phone, I want you to remember all those invisible layers of eye-tracking diagnostics and statistical math engineered into every single pixel just to guide your gaze. Knowing all of that now, how will you look at the next map you open?